Good evening. So today we will go over the triple integral in spherical coordinates. Somewhat similar to the integral, somewhat similar to the double integral in polar coordinates. It is often the case that the Cartesian coordinates are completely inappropriate in some situations. Well, not completely, but definitely not the way to go in certain situations, depending on the domain of the triple integral and or the function to integrate. So I want to go over a couple of preliminary aspects. So first of all, obviously we're going to have to go over what spherical coordinates are and what type of domains are suitable for that type of conversion from Cartesian to spherical coordinates. But I also want to give you a brief justification of why I skip actually when I teach this class usually the cylindrical coordinates, because as it turns out, typically you have three options when it comes to the triple integral: the Cartesian coordinates, which we talked about already before, and the cylindrical coordinates. The reason I don't cover this as a separate section is because we actually kind of know how to deal with them already. We actually used them already in a previous example in the previous lesson. But let's actually define them formally. So if you look at the point in the XYZ plane, in the space, XYZ, you can identify a point instead of using its Cartesian coordinates. You can identify a point via the z-coordinate. So the z-coordinate stays the same, in fact. But instead of x and y, you can choose the polar coordinates in x and y. So in other words, if this distance from, so let's say this is the point P, and project the P over the xy plane, let's denote the projection by m, right? So that's 90 degrees here. So the length of the projection here, let's call it r, and the angle between the positive x semi-axis and OM, let's call that theta. So in this configuration, the x coordinate becomes r cosine of theta. So these are just the polar coordinates, in other words, for x and y. So overall, together with this, and z stays the same, okay? So that's the idea. So instead of identifying the point by x, y, z, you can identify the point by r, theta, and z. But the reason I don't cover it differently, in a separate section in the triple integral is because typically when you split the triple integral in right into a double integral and a simple integral, usually the integral in the middle is in terms of z, and the integral on the outside is the double integral in x and y, which of course you can convert it using polar coordinates to a double integral that is, instead of dr dA, you have r dr d theta, right? So again, I skipped here the function to integrate, but just to give you a refresher from what we talked about before. So again, in a nutshell, cylindrical coordinates essentially combines a Cartesian coordinate, for example z, with this pen here didn't look nice here. So one Cartesian coordinate, let's say z, with polar coordinates in the other two variables. So we know how to do this already because we went over the double integral in polar coordinates. So again, if you use cylindrical coordinates and apply Fubini's theorem, you basically typically do the innermost integral in terms of the Cartesian coordinate, in this case z, and then you have another double integral to compute, which that becomes a double integral in polar coordinates in the other two variables. Okay, so now obviously cylindrical coordinates are suitable most of the time if domains are portions of cylinders or look like cylinders, more or less. full cylinders or portion of a cylinder, right? Those are the most suitable situations. If we talk about domains that look more or less like a sphere, this is what motivates actually the topic at hand, right? The triple integral in spherical coordinates. So let's see how these coordinates are introduced. I mean, how are they defined, and what's the the relationship with the Cartesian coordinates. So let's pay attention here, because it's important, especially when it comes to the bounds, establishing the new bounds in terms of the new coordinates. It's very important to understand how these coordinates are actually defined and the relationship between them and the Cartesian coordinates. So in a nutshell, you can identify the point in space by the distance to the point from the origin and two angles. If you can think of it as an extension of polar coordinates to a three-dimensional situation here. So let's say the point P in question is over here. One coordinate is going to be the actual distance from the origin to the point P. To use the typical notation that you will see in the homework, let's denote this distance by rho. Okay, so rho is the distance between the origin and the point P. And let's project the point P on the xy plane. Okay, another coordinate that identifies the point is going to be the positive angle from the positive semi-axis z. So from the positive z semi-axis, measure the angle all the way to OP and call this angle phi. Again, to use the notation. So phi is going to be the angle between OZ to OP, downward, okay, from your perspective. Let's denote by M the projection of P to the xy plane. Finally, the other third, remember you need three pieces of information to identify the point in space, and the third piece of information is going to be the angle measured counterclockwise from the positive semi-axis to the OM, counterclockwise if you look it from above, right? So that extra angle is going to be theta, which is just like the polar angle, right, from before. So in a nutshell, you're going to have three pieces of information: the distance from the origin to the point P, let's put it in the word, doesn't matter that much, but let's write this in the order that's given in the homework. Theta, the angle made by the projection of the point P to the xy plane. That projection, right, measured from the positive x semi-axis. And then finally the angle phi, measured from the positive z semi-axis all the way to the segment OP. So distance and two angles. Okay, so you'll see with an example why this configuration or this representation is going to be very advantageous in some cases. But for now, let's actually concentrate on let's focus on determining the relationship between the Cartesian coordinates and the spherical coordinates. Right? So rho, theta, phi are the spherical coordinates. Right? I forgot to, just for the sake of completion, write what theta is, right? So it's the angle from OX to OM. All right, so we're going to relate x, y, and z with these coordinates via trigonometric formulas in these right triangles. So if you look at this right triangle, OP and OZ, that forms with the z-axis, notice the z-coordinate is going to be the adjacent side to phi. So the z-coordinate is going to be the hypotenuse, which is rho, OP, cosine of phi, okay, because it's the adjacent side. The projection OM, it's the opposite to phi in the right triangle, okay? So these angles are equal, right, on both sides of OP. You have a 90 degrees angle at M, and OM is going to be the opposite of phi. So OM is going to be, or the length of OM is going to be, again, the hypotenuse rho sine of phi. What about the x and the y coordinate, which I forgot to actually sketch here? What about the x and the y coordinates, right? So that's the x coordinate, that's the y coordinate, right, of the point. Well, in the right triangle that I formed here, the x coordinate is going to be again adjacent to theta. So x is going to be the hypotenuse OM, cosine of theta. But on the other hand, OM, like I said before, is rho sine of phi cosine of theta. And then finally, the y coordinate is the hypotenuse OM sine of theta. And then altogether, rho sine of phi sine of theta. I know it doesn't look like we make things easier, but you'll see immediately with an example that things are indeed easier. So before we turn the page, make sure you write in your formula sheet, those of you who take my classes, the conversion from the x, y, and z coordinates to the spherical coordinates. So x becomes rho sine of phi cosine of theta. Y is rho sine of phi sine of theta. And finally z is rho cosine of phi. Okay, and again, don't forget the notation. Phi denotes the angle from the wall, z, theta is the one from OX. Another very important remark. The maximum range for phi and theta, what is it? Maximum range actually occurs when the domain is in fact a full sphere. Oops, something dropped here. So why do we have a maximum range for these angles? Well, because first of all, rho can have obviously an unbounded range, right? I mean, typically rho belongs to because it's a finite, it's a closed domain, right, for the triple integral. Typically, rho will have constant bounds, let's say a and b, right? But these can be any numbers, right? Again, to make things easier in these sections, by the way, all the bounds for all these three spherical coordinates will be constants. You can make this a little bit more general, but for now, let's focus on that. But what about the maximum range for phi? Well, notice that since theta goes all the way around, can go all the way around the origin in the xy plane, theta is between 0 and 2 pi. Again, not always. This is just the maximum range for theta. Which means phi, and look carefully at the picture, its maximum range is actually only 0 and pi. You don't have to go around 2 pi because that's taking care of theta. So basically, if phi and theta, that's the maximum range for phi. So if these angles go through their maximum range, you're going to basically have a full sphere, okay, of radius rho. So in other words, if your domain is a sphere, it's probably very likely that it's going to be easier to integrate with respect to spherical coordinates. So obviously in practice, we're going to have different situations like, just a piece of a sphere or a half of the sphere, like a hemisphere or a quarter of a sphere, or whatever. And then you're going to modify the range with the domain for theta and phi accordingly. Furthermore, for example, maybe you have a hollow sphere, which means rho will be the in between two positive values, the inner radius or the outer radius, and so on and so forth. But these are the maximum ranges. people sometimes are kind of confused here. Why is phi goes all the way to pi? Because that's all you need to describe the full sphere, basically, the maximum possible domain, essentially, the largest one. Once theta goes all the way around and makes a full circle. And another important remark, which comes very useful later, x squared plus y squared plus z squared simplifies nicely into rho squared. If you want to see the proof, just as an exercise before we turn the page, x squared is going to be rho squared sine squared phi cosine squared theta. Y squared is rho squared sine squared phi sine squared theta. And then plus rho squared cosine squared phi. From the first two, we can pull out rho squared sine squared phi. Sounds very weird, actually, phi theta, but that's the name of them. Let me see if I can fit it in here. The parenthesis becomes 1, right? I kind of have to squeeze it here. I don't want to turn the page before I finish this. But clearly, cosine squared theta, sine squared theta is 1, so the parenthesis turns into 1. And then finally, you can pull out rho squared, and you're left with sine squared phi plus cosine squared phi, which again is 1. So therefore, the sum of these three squares is going to be rho squared. Keep this in mind because in many problems, you're going to see this quantity, this sum of the squares, and make sure you remember that it simplifies nicely to rho squared. All right, so let's move on to the next item before we set up the integral is, what does dv become from the triple integral? Because remember, that's not obvious what it is, and it's not going to be, newsflash, that's not going to be just, d rho, d theta, d phi. So let's stay tuned for the next page. Okay, so what does the v becomes when we switch to spherical coordinates? This is one of those things in which, after I taught this topic several times, I actually won't insist on the drawing as much. So typically when I teach this in the regular classrooms, I am not going to have students actually sketching this. Or maybe I can just give a handout with picture representing this. So it's just far better to just look at the picture here and just listen to the explanation. And again, if you even don't want to do this, you can just go straight to the formula after I go over the explanation. But in my opinion, it's always useful to know where the conversion comes from when you look at the conversion from dv to whatever it becomes in terms of the spherical coordinates when you convert the integral from Cartesian to spherical coordinates. So why the picture? It's by automatically kind of tedious. Well, remember how we actually construct the Riemann integral. Again, this is the same theme, right, for all of these integrals. You're going to make a partition of the domain, right? So in this case, let's say that in spherical coordinates, the solid, which I didn't sketch here. All you see here, by the way, in this little picture is just a little wedge that comes from the partition. So let's suppose that this solid that we have to integrate, the solid E, is given by, so we're going to have to compute the triple integral, right? Let's say of a function f of x, y, z, dv. And then the solid E is given in spherical coordinates by these inequalities, these ranges for rho, theta, and phi. So how does it look geometrically if, like with all Riemann integrals, we're going to make a partition of these coordinates? So with rho, I think it's pretty simple to imagine, right? So a partition of rho is going to give you basically a radial partition from the origin, right? Because again, remember, rho denotes the distance from a point to from the origin to a point on the solid. Now, a partition on the angle theta is going to be represented on the xy plane. So over here, I'm going to make an arrow here. And when you take the limit of the Riemann sum, that little arc is going to be d theta. And that's going to have the effect of giving you the width of this wedge. So again, the partition is going to create a, so let's write it actually in words here. A partition will create non-overlapping wedges. That will actually split the domain. And what you see here is basically a typical wedge. All right, so d theta is going to be the angle corresponding to, let's say, the width, if you want, or one side of that wedge in question. The angle, right? The side of it is basically a little arc, right? So this is the angle. The actual side on the edge is going to be this arc. And at this point, let's actually write down an important formula that we're going to use here. If you have in a circle of radius r, and so a segment of a circle with an angle theta here, the length of the arc, so the arc length on that segment of a circle is going to be r theta in radians, right? So if theta is in radians, the product between the radius and the angle is going to be the arc length. So I don't want to make a mess on the picture here, so I'm going to use arrows. The idea is that this side of the wedge, let me see if I can actually, let me see how can I do this in more, yeah, this side of the wedge, I'm going to use an arrow here, over here, that side is going to be the radius of the wedge, and the radius of the wedge comes from rho sine of phi, because that's the length of the projection from the point to the xy plane, times the angle of that little partition on theta, which is d theta. So the radius of that tiny segment of a circle created by a partition on theta is going to be rho sine of phi. The length of the little arc created by the partition is going to be rho sine of phi d theta. So that's one side of that wedge. We're going to basically approximate the volume like if it was basically a cube, you know, because we're going to multiply all these three dimensions, and that's going to be my dv. So that's the side of that wedge. Moving along, another side which is pretty easy, that's actually straight line, it's not going to be curved, it's just d rho, right? The one that comes from splitting or partitioning rho. So let's see, this one is over here, it's d rho. And then I have one more dimension to compute, which is going to be rho sine of phi d rho, the one corresponding to a split in to a partition in phi, right? The angle measured from the z-axis. So I'm looking at the third side basically that forms the volume of the wedge over here. So this is the last one to compute. The radius of that wedge, of that segment of a circle is going to be rho, right? The distance to the point. And then the angle is going to be the change in phi, which comes from the partitioning the interval that gives you the range of phi. So that's going to be d phi. So when everything is said and done, that wedge volume is going to be the product between the three dimensions. One arc of length rho d phi, another arc of length rho sine of phi d theta, and finally a straight line which is just the change in rho, which is d rho. Okay, so when we rearrange these steps, that's going to be my dv. right? dv in the new coordinates. So when we convert from Cartesian coordinates to spherical coordinates, to recap, x becomes rho sine of phi cosine of theta, y becomes rho sine of phi sine of theta, and then z is rho cosine of phi. And dv becomes, if you rearrange the terms here in the wedge volume coming from that partition, rho appears twice, so it's rho squared sine of phi, and then d rho, since the bounds are constants, the order of integration doesn't matter, so it's d rho d theta d phi. Typically we do it like that. It doesn't matter actually if the bounds are constant. If they are not constants, of course, the order of integration matters. But these are the substitutions you need to perform when you move to spherical from Cartesian to spherical coordinates. So just like in the polar coordinates, when you had that extra r, this time around you're going to have an extra rho squared sine of phi, which comes from this computation. So therefore, let's write this as a formula before we move on to the next page to go over a couple of examples. So in spherical coordinates, your triple integral over the solid E of a function in Cartesian coordinates f of x, y, z dv is going to be the integral from, in this order, from, what did I say? So c to d, those are the bounds of phi, alpha to beta, those are the bounds of theta, and a to b, in my notation, the bounds of rho. Then in the function, you're going to replace obviously x with rho sine phi cosine theta, y with rho sine phi sine of theta, and then rho cosine of phi, and then dv becomes rho squared sine of phi d rho d theta d phi. I'm going to have to actually write this on the second page as well. But anyway, this is the formula, and then let's proceed with, I think we'll see 2 examples should be fine on the next page. So stay tuned for the next page. All right, so our first example, let's compute the triple integral over the solid E of the function x e to the power x squared plus y squared plus z squared dv, where e is the, let's say, the unit ball in the first octant, like in the positive region of the space. It's an 8th portion of a sphere, basically, right? So if you were to sketch this, it's going to look like that, right? More or less. Again, once you visualize the object and you can figure out the bounds quickly, then you don't have to sketch too much. So, because this is a portion of a sphere, right, the solid in question, and because the function also contains this x squared plus y squared plus z squared, these are strong clues that spherical coordinates are the way to go. And let's say, first of all, carefully what the domain is in spherical coordinates. So first of all, obviously rho is between 0 and 1. It's a solid sphere, right? Nothing hollow, it's just the unit ball. Right? So that means the radius is 1, rho goes from 0 to 1. Next comes theta. Theta goes over a quarter of a circle in the xy plane. So therefore theta runs from 0 to pi over 2, 0 to 90 degrees. Finally, phi goes from the, if you follow my arrow here, goes from the positive z-axis all the way to the xy plane. That's also pi over 2. So phi is between 0 and pi over 2. Okay, so that's the solid E. And by the way, notice that the simplification is tremendous. Even before I actually solve the integral, I know this is going to be easier, simply because I have constant bounds. Just to put this in perspective, I'm going to write this in the corner. If you insist on Cartesian coordinates, the equation of the sphere is this. one of the bounds is going to be square root of 1 minus x squared minus y squared. Who knows what the integral is going to look like if I have to plug in that bound. I mean, the next integral after I solve the innermost one. So constant bounds are always easier, obviously, than variable bounds. So now my triple integral then becomes the integral from, like I said, let's use the order d rho d theta d phi, doesn't matter, but just to keep up with that notation on the top. 0 to pi over 2, 0 to pi over 2 for the other angle theta, and then 0 to 1. And now I have to be careful with substitution. X becomes rho sine of phi cosine of theta. Let me think a little bit. I want to make it yeah, sorry, I want to make it different. Let the problem, just a little modification here. I want x squared plus y squared plus z squared, because it's not gonna I don't think it's gonna work the way I like it. Yeah, let's make it to the power 2 here. Just a little modification here. Okay, so it's x e to the power x squared plus y squared plus z squared quantity squared. And I don't know if actually that makes much of a difference, but okay, let's leave it like that with this modification. So x squared plus y squared plus z squared, remember, in spherical coordinates, that's rho squared, right? So that's going to be e to the rho squared quantity squared. And again, dv, remember, it's another rho squared sine of, yeah, that's why I wanted that, because otherwise it's hard to compute. So dv is rho squared sine phi d rho d theta d phi. All right, let's actually simplify this a little bit. If you look carefully, everything splits into a product of functions in rho, phi, and theta. So the terms in rho combine into rho third e to the rho to the power 4. Then I have a cosine of theta by itself, and I have 2 copies of sine of phi. D rho d theta d phi. If you remember from previous topics, since I have constant bounds and everything splits into a product in the 3 variables, the triple integral becomes the product of 2 single variables Riemann integrals. The one in theta, the one in rho, is rho third e to the rho fourth d rho. The one in theta, it's cosine of theta d theta. And then finally the one in phi, sine squared of phi d phi. Okay, we still have to do some work. Okay, it's easier than in Cartesian, but it's still not, I mean, we still have to do some work. It's not always straightforward. To integrate sine squared, remember from calculus 2, here we need a double angle formula. You need to replace sine squared with 1 minus cosine of 2 phi. 1/2 minus 1/2 cosine of 2 phi. The double angle formula. Let's actually do the first 2 integrals. The first one works by substitution. U equals rho to the power 4. Du is 4 rho third d rho. And then the new bounds. So if rho is 0, u is 1. If rho is 1, u is 0, u is 1. Right? So the bounds are the same in u. The first one is the integral from 0 to 1 e to the u du over 4 from that substitution. Middle one is just sine of theta between 0 and pi over 2. And then let's do it in 2 steps. And so the last one is going to be the integral of 1/2 minus 1/2 cosine of 2 phi. We're going to integrate it at the next step. First integral is 1/4 e to the u between 0 and 1. The middle one is actually just 1, sine of pi over 2 minus sine of 0. And the antiderivative of the last one is 1/2 phi. Integral of cosine of 2 theta is sine of 2 phi over 2, right? So it's minus 1/2. Another 1/2 makes it 1/4 sine of 2 phi between 0 and pi over 2. All right, so the first parenthesis is just, it's 1/4 e minus 1/4 times 1 e to the 0. Middle one is 1. And then the last one is 1/2 pi over 2 minus 1/4 sine of pi, which is going to be 0. And then 0 minus 0, right? Because it's sine of 0 is 0. So we have e minus 1 over 4, sine of pi is 0, pi over 4. So it's pi over 16 times e minus 1. Okay, so I think this example kind of has everything. We're going to do another one, which reminds me actually, before I do the next example, the last example on the next page, that I forgot to mention something important in terms of an application of triple integrals. But I'll do that in a moment on the next page. Okay, so the remark I wanted to mention is that, I mean, one quick application of the triple integral. If you integrate, so if you compute the triple integral of the constant function 1 dv, this integral represents the volume of the solid E. So again, if you understood how this is defined, it should be pretty obvious why that's the case, because remember, you evaluate the function at an intermediate point, and then you multiply, when you do the Riemann sum, and multiply by the volume of the piece of the partition, and then basically add up all these pieces and then take the limit. So in other words, in the limit, you basically add up all those non-overlapping pieces of the solid, and then of course what you get is going to be the volume of that solid. So as an immediate tool of finding the volume of a solid, obviously a closed solid, is simply to take the triple integral of 1 dv. So the function to integrate is just 1, which is a function like any other function. It's nothing special about it, except that is probably easier usually because you don't have lots of stuff to compute. I mean, obviously the innermost integral is straightforward. The other two, that's a different story, but at least the innermost one is going to be always immediate, because it's just integrating 1 with respect to one of those variables. So actually, let's use this this application to solve another example with spherical coordinates. So let's say we want to find the volume. So find the volume of the solid within the sphere given by, so one bound of the volume is the sphere given by x squared plus y squared plus z squared equals 4. And above the cone z equals square root of x squared plus y squared. And yeah, I think that's it. Yeah. So it's essentially just like ice cream wafer, more or less, right? So we have, let's see, we can give a little sketch here. Okay, let's actually visualize the cone first, kind of like that. And we're gonna have a sphere. So, okay, so the solid is within the sphere and above the cone. So let's emphasize the actual solid in question. Like that. By the way, you could also set it up like a double integral if you remember our previous topics, because you can visualize it as a solid between a top surface and a bottom surface. So you could do that, but with the top surface given by the sphere and the bottom surface given by the cone, and then you have to find the domain, the common domain, and so on and so forth. But let's actually do this via a triple integral over the whole solid here. So the triple integral of 1 dv. However, let's figure out first of all the bounds of integration, right? Here we have to be, again, we're going to be a little bit careful here. So the bounds for rho should be pretty straightforward, right? It's from 0 to 2. The radius of the sphere is 2. So if you look at the all the segments coming from the origin to any point on the solid, the range for that variable, which is rho, is just 0 and 2. Secondly, the range for the range for theta again is pretty straightforward, because you go all the way around the origin. Theta, which remember it's the angle made by the projection with the positive semi-axis, is 0 and 2 pi, is the maximum range for theta. Now, what about phi? That's going to be the one that you have to be careful, so you can compute the measure it carefully. In order to figure out how far you go from z downward, right? In order to figure out this angle, I need to figure out the point of intersection between the sphere, not the point, the region of intersection between the sphere and the cone. And I'm going to look, obviously it's going to be a circle parallel to the xy plane, and I'm going to look at the z coordinate of that point so I can tell the angle phi that goes from the positive z-axis. So let's find the intersection first. So obviously I can look at these two as a system, the two equations, and try to eliminate z, for example. Okay, and then I can square the first one, plug it into the second one. So for example, x squared plus y squared is z squared, plus another z squared equals 4. 2z squared equals 4. That gives me z squared equals 2. We live in the z is positive, clearly from the picture, and that means z equals square root of 2. Okay, so I know that the coordinate of this point, right here on the circle here, well, I should say over here, right? That coordinate is square root of 2. Which means, let me actually use a different color here, which means what you see here, it's a right triangle with 45 degrees angles, right? If I have to copy this, if I take a cross section, this is square root of 2, and because the radius is 2, from Pythagorean theorem, I know this is also root 2. Or you can just use basically a trigonometric function, right? So for example, I look at the opposite side of this angle divided by the hypotenuse, and I ask myself, this is, the inverse sine of what angle actually, right? So that's going to be obviously a 45 degrees angle, or pi over 4. Okay, so that tells me the range for phi, right, is going to be from 0 to pi over 4. Okay, let's write it here on the top. 0 less than phi less than pi over 4. So these will be the bounds in my triple integral. So with this, we can proceed with setting up the triple integral. So the volume in that we try to compute, 1 second, so the volume of the solid E is going to be the triple integral of 1 dv over E, which now in spherical coordinates is from 0 to pi over 4 for phi, from 0 to 2 pi for theta, and then from 0 to 2 for rho. 1 times dv, but dv becomes rho squared sine of phi t rho d theta d phi. Once again, this splits into a product of 3 integrals. The theta doesn't appear anywhere, so the integral in theta is just 1 d theta. The one in phi is just the integral from 0 to pi over 4 sine of phi. And then finally the one in rho is just rho squared d rho. So we have theta between 0 to pi. Integral of sine is minus cosine of phi between 0 and pi over 4. And rho 3 over 3 between 0 and 2. 2 pi minus cosine of pi over 4, which is root 2 over 2, plus minus minus plus cosine of 0, which is 1. And then 8 over 3 minus 0. Alright, so when everything is said and done, I'm going to have, so these two combine into 16 pi over 3, and then 1 minus root 2 over 2 in parentheses. And we can leave it like that. Alright, so that concludes this section and the chapter 15. Our last unit is going to be on vector fields, which is again the most general type of function that we're going to deal with this in this class when the function takes a vector and then returns another vector. So that's it for today. I'll see you next time.